Oh, sorry, I thought it's not recording, but anyway, let's quickly focus on this question number 3. So let's redo it again. So let's redo this question number 3, but before we do question number 3, let's quickly focus on how to get the work done by gravity. Right. So we have different types of what incline. We have a flat one, then we have what a vertical one, and we have what incline one. Right. So on a flat surface, we know that forces that act perpendicular normally going to be the what? The normal force and your Fg, they will do what? They will produce what? 0 work done because of the angle cos 90. That is clear, right? So forces that act perpendicular on a surface always carry this thing. The forces that act perpendicular to the surface, they will do what? The work net thing, it will be 0. So in the vertical one, maybe they can say obviously Fg is there. Maybe other forces, maybe a hanging object most of the time. Now happy, you must be careful happy, got the delta as delta y. The distance that your object covers. So let's say I want to say delta y. If let's say delta y1, meaning that maybe that object they drop it from the height of that particular thing, and then when I hit the ground, so Fg is always down. Then if maybe this thing they throw it to the height or they pull it up, meaning that now your delta y, it will cover that in direction delta y2, meaning that this you must be careful or where does your delta y is covered because of the angle matters. So if now you're using delta y, maybe that things they release it from a height. That means that when I look at it, the angle that is between your Fg and the angle that is between your delta y, you can see that it will be what? Cos of what? Cos of 0. Then if that thing is going up or they pull it in upwards, you can see that between this and Fg and that delta y, your angle there will be what? Cos 180. Okay. Then in incline, we know Fg is always downward. Then now, if we resolve it into each component, you're gonna have what? Fg parallel. Let me do this. Fg parallel, and also Fg what? Perpendicular. But Fg perpendicular as well as the normal force, they act 90 to that. So see like here, and then meaning that the work done by the normal force and the Fg parallel, they will be what? 0. Then now to calculate your Fg parallel, is either, the work done by Fg is either use Fg parallel or Fg as Fg. So let's quickly focus on Fg. You're gonna say a work done by the Fg equals to what? Fg sine delta x cos theta. And remember that Fg parallel, it has the mass, gravity, and the sine of what? Sine of the theta. This sine theta, or rather this theta, is the angle of your incline. Let's see here they give you 25, then you're gonna use what? 25 degrees is the angle of the incline. And see this one, you know that it will be the angle of what? Between your Fg and your delta x. So let's say the Fg parallel is facing that way, and now while the object goes up, you can see that means that the angle that you're gonna use is 180. Then let's say we have FG like this, and then now our delta, or rather they release that object. You can see that so see the angle that is between FG and your delta x, it will be 0. Okay, then also remember that your incline is your what? Your delta x. Now allow me to erase this part so that I can create a space. So now we're looking at FG. If we're using FG, and you saw that FG is what always done downwards, so you're gonna say work done by the FG is equals to what? FG delta y cos of theta. The reason I say delta y is because of your FG face what? Downwards. So meaning that downwards delta y is normally the opposite side here. That is your delta y. So to get this side, normally you can normally use your trig functions that SOHCAHTOA, but I make it simple for you. To get that delta y, you can see that delta y is equals to sine theta delta x, meaning that when we say sine, the angle of we are given in incline, delta x, this angle that is given to calculate work done by the FG. So let's quickly redo this question number 3. So they say that a man pulls a cart with a load up a hill which form an angle of 25 with the horizontal. So the mass of the cart and the load is 350 kg, and which experience a force of what? Frictional force of 180 newtons. And this man walk a distance of half a kilometer, meaning that a half kilometer, remember that we are dealing with meters, so we know 1 kilometer equals to how much? 1000 what? Meters. But if you say half kilometer, that means that you're gonna half kilometer, you're gonna divide this by 2 or multiply by 1/2, and then you get what? 50 meters. That means that this is our delta x that you're gonna use. So also at a constant velocity. So obviously, if the men work a distance of 500 meters, also the box, the cart will also do what? Covers that distance. Then let's quickly answer this question. They say that we must draw a free body diagram. So when you're drawing a free body diagram, the man pulls, force applied, Fk. Okay, that is Fg, and then this is your normal force. Right, this is your free body diagram. Then let's draw the one that you resolve your Fg into each component. So you're going to have what? Fg, force applied, Fk, Fg parallel, and you have what? A normal force, and also we have Fg perpendicular. So we know Fg perpendicular and Fg normal force, or rather work done by the normal force, and work done by the Fg perpendicular, it will give you 0. Why? Because of the x 90. That is the angle that is between your force and displacement. It is 90. Alright. 3.2, they say that determine the net work done by the cart and the load. Constant velocity, meaning that your work there will be 0. And also it means that your network, it will be what? 0. Right? And then to calculate the net, or other, because the following question, it needs that you calculate the work that the man does on the cart and the load. So basically you can say a work net is equals to 0, whereby you equals to the work of what? Force applied plus the work net by FG parallel plus also work done by the FK, right? Let's quickly do it. You're going this 3.3. So work done by force applied, you are looking for 8 plus we know FG parallel is going to be, let's make a bracket. Let me write it here. It will be what? M plus G sine of what? Sine of the theta. So basically you can say 350 times what? 9,8 times sine of what? Sine of what? 25. Right? Sine of 25, and it's going down, meaning that you're going to use cos what? Cos 180. Then multiply by 500 is your delta x, and cos of what? 180, close bracket. Maybe I'm supposed to use this one, close bracket, and work done by the FK, it will be 180 times 500. I don't have a space. That you're gonna multiply with what? Cos of what? Cos of 180, also cos of FK is downward, but you cover your displacement up, so therefore equal to what? 180. Then we have work done by the force applied. Then if you punch your calculator, you will get negative 814,790,32. Then you transpose that, and then we have work done by the force applied will be what? 814,790,32 newtons. Oops, joules. All right. So remember also I said in that previous video that if we see that the constant velocity can go from work net by the net force, meaning that you have to look for the F net delta x cos theta. That means you have to look for the F net. So let me erase this part. Okay, let me not erase the answer. I'll just show you something. So now when you look for the F net, they say that constant velocity, it means that your force are equal. The one that goes up is equal to the one that goes down, meaning that this, remember, let's say F net is equals to 0. This, so sorry, okay, so force applied, it will be equals to what? Your FK plus your what? Your FG what? Parallel, right? So it does mean that you can easily get the force applied there, meaning that your friction you know is 180 plus here we know that you're gonna resolve it by saying mg sine of what? Sine of the theta. Then you're gonna say 350 times 9,8 sine of the angle of the incline 25, and then I believe that you will be able to get 16,629,58 joules. No newtons. Why I'm making mistake, right? Newtons. And remember that is a vector. Then we say up the incline, so that you can know where it's going. And also the free body state that. Then you come back from that. You have the work net, and we're looking for work done by the sorry, we are looking for the work done by the force applied. So you can say work done by the force applied, it will be what? Force applied delta x cos of what? Cos of the theta. Then you say 16,000 6,629,58. Then your delta x half a kilometer, which is 500, and we're going to multiply by cos of what? Look at the angle, cos of 0. Then I believe that you are getting 814,790,32 joules. Thank you.